Good day, and welcome to our webcast today. This is transforming nutrient removal and water resource recovery facilities through suboxic/low DO treatment. This webcast is part 2 of a 3-part webcast series on this specific topic. If you weren't able to join for part 1, no worries. While part 1 might be helpful background for this particular webcast, it's by no means a prerequisite. If you, after participating in today's webcast, if you would like to view part 1 of the webcast series, it is available for viewing on demand on the Water Research Foundation website. So this is the title for our part 2 of this webcast series session. It's titled Aeration System and Control System Design for Low DO/Suboxic Process Operation. My name is Jeff Moeller, and I'm a Director of Research Services at the Water Research Foundation, and I'll be serving as the moderator for today's webcast. I'm briefly going to go over a few housekeeping items, as well as provide a high-level overview of the agenda, and then I'll hand it off to our first speaker. So in terms of housekeeping, please submit questions through the question box at any time. We'll do a Q&A at the very end after all of the presentations are done, but please keep your questions coming throughout the webcast. Slides and a recording of the webcast will be available at WRRF.org. You can download the slides now under the event resources on the bottom left of your screen. So these are available to you now. A certificate of completion will be automatically generated after the webcast. And if you have any questions, please contact Michelle Suazo at the email shown on your screen there. And then lastly, we'd encourage you to stay on until the end to fill out a quick survey with your feedback on the webcast. Here's our agenda for today's webcast. After the welcome and housekeeping, our agenda is divided into 3 sections. First, we have an overview of design considerations for low DO/suboxic process operation, and that's going to be presented by Natalie Beach, lead technologist at Carollo. After Natalie, Steve Kestel, Director of Advanced Aeration Controls at APG Neuros, will provide an overview of blower considerations for low DO operation. And then after Steve, Alex Exter, Technical Director of Exter and Associates, is going to cover advanced DO and SRT controls. After all of our presenters, we'll leave time at the end for discussion as well as Q&A. And here's our presenters for today, Natalie Beach at Carollo, Alex Exter at Exter and Associates, and Steve Kestel at APG Neuros. Their full bios are available to read on the bios tab, so I'm not going to read through those now, but they're available to you to read. And then their contact information is shown on the slide here, so if you'd like to follow up with any of them after the webcast, you are welcome to do so. Okay, and with that, I'd now like to hand it over to Natalie Beach.
Thank you, Jeff. So we'll start off with a high-level overview of design considerations for low DO and suboxic process operation. As Jeff mentioned, this is one of a series of 3 webcasts. If you haven't seen it already, I recommend going back to the recording of the first webcast where Tanya Rock-Williams and Daniel Noguera present an overall introduction to low DO and microbial fundamentals. Today, we'll focus on aeration system and control system considerations. And I also highly encourage you to tune into the final webcast in this series on November 19th, where our team members from Los Angeles County Sanitation Districts will dive deeper into the Pomona water reclamation plant site-specific operation, performance, and lessons learned from the full-scale demonstration. And this project would not have been possible without the award from the Department of Energy. So here I'd like to acknowledge all of our team members and collaborators listed here. So let's get started. Now, this is a conceptual overview of a MLE configuration, which is how the Pomona water reclamation plant is configured with basic aeration and control system components. You'll see this slide throughout my section because I use what's on the left as a table of contents and of what I'll be discussing. So a high-level overview of each item. I'll discuss considerations for process monitoring and instrumentation selected for this project, with Alex providing more details on the aeration and the SRT controls at the end of the webcast. I'll also touch very briefly on blower considerations, with Steve providing more details on blowers after my section. And I'll also talk about the specifications of valves and actuators, what we did with the diffusers, and swing zone operation. So as most of us know, controlling DO and activated sludge is no easy task, especially in plug flow processes, because process response is nonlinear, such as reaction rates are relatively slow, and site-specific factors can vary quite a bit. There are many factors that impact control response in aeration basins, including the wastewater characteristics themselves, such as loading, temperature, total dissolved solids, which affect your DO solubility and microbial activity, and then of course, diurnal and seasonal changes. There's also the operating characteristics that include your hydraulic residence time and solids retention time. Also the system components like the aeration basin configuration, diffuser layout, and diffuser condition. And then of course, the process monitoring and components directly affect control response. These are your probes, how many you have, where are they located, and their accuracy and response time. So when it comes to control approaches, we know that there are a variety that are currently used for low DO operations around the US with varying control performance. There are plants that operate with each of these strategies that do achieve low total inorganic nitrogen effluent quality. I'm not here to dive into what each of these are or to compare them, but I want to highlight that in this study, our goal was to provide a proof of concept of machine learning control for Suboxic operation, and Alex will go into more detail on this and the performance at the end of this webcast. So what exactly does it mean when we say we want to maintain good control? An example goal could be that you're trying to consistently maintain a particular target dissolved oxygen concentration, or maybe an ammonia concentration if you're operating in ammonia-based aeration control mode. There are several parameters to think about when we talk about control and the instrumentation we may be considering, like accuracy, or how close the measurement is to a standard value. Precision measures how close a set of measurements are to each other when repeated over time or with different people, and repeatability is a component of precision. Repeatability measures the variation in measurements taken by the same instrument under the same conditions. Response time, or time constant, is how quickly the sensor reacts, or the time it takes to come into equilibrium with the true value. So I bring these up because I want you to keep them in mind as we review the specifications of instruments that were selected for the full-scale demonstration at Pomona. All right, so here we have a table that summarizes the instruments selected for the demonstration at Pomona, which all had high accuracy and high repeatability. And although the equipment and controls that were selected in this project did lead to highly accurate control and energy savings, as you'll see in this webcast and the next, we present this information not to suggest that you must have these instruments to operate at low DO or Suboxic systems, nor to specifically endorse any equipment, but we want to provide information that can serve as a benchmark for facilities that are interested in achieving a high level of process control, as Alex will dive into and demonstrate at the end of the presentation. This table of information will hopefully give those interested in low DO operations something to compare to when looking at options and speaking with manufacturers. For example, thermal mass airflow meters that were selected in this project had a high accuracy of 1%, a repeatability of 0.25%, and a fast response time or time constant of less than 1 second. The fluorescent DO probes, ammonia, ion selective electrodes, and TSS probes were also selected for their high accuracy, repeatability, and response time or time constant. So not only is sensor selection important, but the number of sensors installed can also be important. In the case of DO, the profiles are dynamic in plug flow processes and change in response to load variations throughout the day. Multiple probes can also provide design and operational guidance based on DO profiles during low to high loading periods. As shown in the figure on the right, this has a DO profile and what it could look like across an aeration basin during periods of low loading, as in line number 1, or high loading, line number 3, and conceptual vertical dashed lines show where multiple probes could be placed to give the full picture. Multiple probes can also give the ability for early detection of high loads during low DO, and this can help you prevent reaching DO depleted conditions. It can also help optimize airflow control and confirm process performance. So many facilities only have one DO probe per basin. Obviously, this is the most inexpensive option when compared to full monitoring, but it doesn't allow you to see the DO profile across a basin or how it changes throughout the day or week, like I mentioned previously. The risks associated with this are over-aeration, inefficient energy use, and DO sags, which can lead to incomplete nitrification. Avoiding sags and DO becomes even more important at low DO and suboxic conditions because you're already at the lower end of DO concentrations. The other side of the coin is full monitoring, which is great, but it comes at a cost in terms of capital and O&M. It does allow you to see profiles across the length of each basin, and this can be important for some facilities with low nutrient limits who also have an uneven flow and load split between their basins. For example, the extensive instrumentation used at Pomona really highlighted their uneven flow split and how one of their basins was impacting their overall performance. But again, it's more expensive. To split the difference, some may consider hybrid monitoring. So what this means is you'd be providing full monitoring in some basins to use as a guide for control in your other basins. This could be a good solution for facilities that have a relatively even flow and load split to balance cost and performance, but it may not be a good fit for facilities with that uneven flow and load split that we talked about previously. All right, so some other instrumentation and monitoring takeaways. Instrumentation providing real-time readings can be a huge help. They allow plant staff to see diurnal peaks that can impact your effluent quality. For example, at Pomona, they were able to detect and track diurnal changes to ammonia throughout the day and week and react accordingly, adjust their controls to help them drop their effluent ammonia as they needed. With regard to ammonia sensors, it matters where your ammonia probe is placed. For example, you don't want to stick it right at the end of your basin where your concentrations are the lowest. And if you're operating in ammonia-based aeration control mode, ammonia sensor repeatability is really critical, especially at those low ammonia levels. Nitrate sensors are something you might want to consider as well, adding to your process if you're operating at low DO or suboxic conditions, since it can promote simultaneous nitrification and denitrification. And some control systems like ammonia versus NOx or AVN require them. And finally, phosphorus is also worth monitoring when operating at low DO or suboxic conditions because some plants can actually slip into biological phosphorus removal even if they aren't designed for it, which can lead to struvite issues. So it's a good idea to monitor, even if just with grab samples and even if you don't have to treat for it. All right, so next up, let's talk very briefly about blowers, and Steve will dive a lot deeper into this after I'm done. So one critical consideration for blower selection and system design for low DO is the required turndown, which is not a surprise. Facilities interested in retrofitting their process are not going to be operating at low DO from the get-go and will need to be able to get and provide enough airflow for high and low DO conditions in their aeration basins. And for example, some facilities in colder climates may even consider switching back and forth between lower and higher DOs seasonally as a strategy to combat nitrification issues in the wintertime and at low temperatures. And we have some data that supports this from a facility. And all of this plays into the decision for how much blower turndown is required for a specific plant. So this graph shows in red or orange, depending on your screen, in the dots, the total aeration airflow at Pomona over a 2-month period in 2022 when they were operating at a higher DO concentration with an average of approximately 2 across the entire basin length. The green dots are the same 2-month period, so August to September from this year when they were operating at an average of approximately 0.8 milligrams per liter. And on this graph, I highlight the peak hour airflow at their high DO condition, which was approximately 12,120 SCFM, and then the minimum hour airflow at low DO of 1,800 SCFM, which establishes that 85% turn down needed to be able to operate at these two conditions. And on the pop-up that just came up, a typical blower has a maximum turn down of around 50%, but a well-designed system with multiple blowers can achieve a system turn down of 80% or higher. Again, Steve is going to cover important considerations for blowers and blower selection after this section, but I wanted to show what Pomona would need in terms of turn down to meet the high and current low conditions, not including if they want to drop the DOs even lower. So now let's talk about the airflow control valves and actuators. In this project, spoiler alert, we were able to demonstrate that butterfly valves can work well at low DO with the right control system, even though iris and jet valves are selected for their larger operating ranges and have higher accuracy and repeatability. So here we have a graph showing the operating range of each type of valve, diaphragm or iris valves represented with the blue line, jet valves in the red line, and butterfly valves in gray, with jet valves having the most linear and largest operating range. However, the valves with the larger operating ranges require a larger capital investment. Pomona installed butterfly valves with electric actuators to control air to each of their grids, and we were able to show that despite butterfly valves having a limited operating range, they can work really well and have tight control at low DO when paired with the advanced control system, which Alex will talk about more later in this webcast as well. Now, with regard to actuators, ones with high accuracy and unlimited movement were selected for Pomona. The unlimited movement was critical to stay ahead of the change in airflow requirements diurnally. These electric actuators have a very low time delay of less than 0.1 seconds, a rapid response time, and high position accuracy as shown in the table. Again, this information is not to endorse specific equipment, but to give you a benchmark when you start to talk to manufacturers and you want to compare it to another process and condition. And Alex will show how all of this led to the performance results with his controller at the end of this webcast. All right, next up, diffusers. Here we summarize diffuser information at Pomona from diffuser type, diffuser counts per zone, air loading per diffuser at average and minimum conditions, and airflow provided for mixing for the Pomona site at their high DO operation, modifications for low DO, and a column at the very right-hand side that summarizes what we would have done in hindsight now that we're at low DO conditions. So at Pomona, prior to this project, they operated with 9-inch ceramic discs in their 3 aeration grids. Grid A is their swing zone. Grid B and C are their dedicated aerated zones. The decision was made to switch to 9-inch membranes to give us the option to operate with intermittent aeration if we needed to once low DO concentrations were reached. You also see that they plugged several diffusers before the transition to low DO, as shown in the 4th through 6th rows of this table, with an 18% reduction in the swing zone, 13% reduction in grid B, and 42% reduction in grid C. The average air loading per diffuser in grid B and C, using the data from our lowest DO operations, so that same 2 months I was talking about previously, was about 1.6 to 1.7 SCFM per square foot of diffuser. And the minimum is currently at about 0.6 to 0.7 SCFM per square foot of diffuser. The airflow provided for mixing that we typically aim for based on like the rule of thumb, based on like Metcalfe and Eddy values, is around 0.12 SCFM per square foot, but we know from other studies that we can get sufficient mixing at some sites at half of that value. Here at Pomona, we're seeing anywhere from 0.06 to 0.13 SCFM per square foot in the 2 aeration grids B and C without any obvious issues. Now, when we first started this project, the operators were pretty nervous about making such a drastic change to their diffuser counts, and they didn't feel comfortable reducing the diffusers by what was originally recommended, especially in grid B, which is their first dedicated aeration zone. But if they could go back, LACSD staff agreed that they wouldn't reduce the count in the swing zone, which is what was recommended initially, since they maxed out their DO currently at about 0.6 milligrams per liter with their valves fully open. If they didn't reduce their diffuser count in the swing zone, then they'd probably be more aggressive with the diffuser reduction in grid B and not make a change to grid C in order to balance out the air demand and enable them to more consistently achieve lower DOs than where they're at now, to encourage more biological acclimation. Some still question, though, if your typical fine bubble disk diffuser is the best option. But as mentioned on the last slide, there have been no apparent issues at low DO at Pomona with them, although we may have decided to be a bit more aggressive in the diffuser reduction at the beginning. Some facilities that are looking to replace their diffusers, they may consider floor-mounted panel diffusers, since mixing limitations can happen between that space as shown in the upper right photo, between the floor and the diffusers themselves, which can lead to sludge and solid accumulation, loss of tank capacity, and can negatively impact chemistry of the aeration process. But again, we have seen no apparent issues at Pomona. Some other design operational flexibility alternatives for low DO that may be considered include designing for more than one aeration grid per zone, as you can see in the photo on the right. So you can turn one grid on or off to meet minimum to peak aeration conditions. You could also take basins in and out of service and consider diffusers that allow for higher flow ranges. And finally, let's talk about what we do about swing zone operation. So some facilities have swing zones as part of their process, and swing zones are basically zones that are designed with mixers and diffusers so they can switch from being part of the unaerated zone volume to the aerated zone volume for operational flexibility. Pomona has a small swing zone that's about 13% of their total aerated volume. They did aerate this zone during the transition to low DO to improve the aerobic solids retention time and the aerobic hydraulic retention time for nitrification. Today, they do still operate this zone at the lower DO concentrations, but only between about 7 a.m. and 2 p.m. when their diurnal loads are the greatest. Although plant staff aren't certain how much this has helped with nitrification, we do believe it gives a head start to the DO in the first aeration grid, but they have noted that it may have negatively impacted SVI. I will also note that they've mentioned that the reduced unaerated volume has not affected denitrification. But now that we're nearing the end of this project, we plan to run a test to turn off the swing zone and see if there's any negative impact to nitrification or positive impact to SVI to test our hypothesis. And with that overview, I'd like to turn it over to Steve Kestel to give us a focused discussion on the blowers.
Thank you, Natalie. When it comes to blowers, there are a number of different options that are available in the marketplace. There's 4 main different types of blowers that are available, whether they're positive displacement, multi-stage centrifugal, single-stage centrifugal, or high-speed turbo. Within those, there's also some different variations, particularly within positive displacement. There's pretty large differences between different types of positive displacement blowers that are available, whether that's tri-lobe, twisted lobe, or screw-type blowers. When it comes to the single-stage centrifugals, integrally geared turbo are available, and high-speed turbos. There's different types of bearings that are available, whether it's air bearing or magnetic bearing, and then you can also get high-speed turbos in a single core or a dual core configuration. All those different types are going to respond differently to the needs of low DO operation. And so we're going to kind of go through over my next portion of this presentation what we really want to be looking for in our blowers to help you better choose which technology might make the most sense for your particular application. The 3 main factors for selecting the blower, particularly for low DO operation, are turn down, as Natalie mentioned. There can be a very large difference between the minimum and maximum airflows needed on any given day. So a blower technology that has a wide turn down is really going to be a key factor in making sure that you can achieve the airflows that you're looking for under all conditions. And keeping in mind that you have to meet both present day low loading, potentially low DO concentrations, all the way to, in the future operation, you might want to go back to higher DO operation, and also high loading, high flows, high concentrations, 20 years in the future for design. So you need a blower system that can cover all that. The second factor that's key for low DO operation is controllability. So as Alex will talk about, if we want to maintain very precise control, potentially we could need very quick, rapid control actions that really tightly maintain those dissolved oxygen concentrations right on their set points. And lastly, it's always important to consider the efficiency of the blowers. One of the main goals of the low DO operation is to reduce energy costs. So you want to select a technology that can be as efficient as possible. Higher efficiency is always going to be better. Looking at turndown, as Natalie did focus on at Pomona, we saw a very big difference potentially between the high and low DO operation. This chart is from a separate plant. Again, just reinforcing that fact that on any given day, there can be a very big difference between the minimum airflow and the maximum airflow required. This chart shows a 7-month period from this year, where it shows the red line is the daily high airflow measured at that site. Blue line is the daily minimum flow, and the green line is the average flow. So that difference between the blue line to the red line is the daily turndown requirement. If we look at the ratio between the two, we can see that on average, it was anywhere from 2 to 3 to 1 turndown requirement, with it peaking as high as 4 or even 5 to 1 turndown requirement, where 2 to 1 turndown would be 50% of maximum turndown, all the way up to 5 to 1 would be a 20% of operating output. Again, within all those different blower types, they each have a very different amount of turndown that they're able to achieve. These lower numbers are somewhat approximate. Different manufacturers are going to be able to tweak their specific technology a little bit differently, but they do kind of give you a general sense of what each blower technology is capable of. So if we start up at the top, multi-stage centrifugal blowers historically have the worst turndown, usually only being able to go down to roughly 60% or so of their maximum output. That can often leave then a flow gap with multi-stage centrifugal blowers, where if you need to get to say 55% turndown, one blower might be too much, or 2 blowers might be too much, and 1 blower is not enough. So there's a gap that you really want to be aware of. And if you're in that gap, that's not going to allow you to hit your airflows, which then is going to lead to your DOs being off their set points. Moving down from multi-stage centrifugals, interleague geared single-stage centrifugal blowers and high-speed single-stage turbo blowers often have pretty similar turndown capabilities, roughly 40 to 45%. PD blowers historically do have the greatest turndown. Tri-lobe PD blowers can often achieve turndown all the way down to 25% of maximum. Screw type blowers can go down even a little bit further, often to 20% of maximum. And then the last option, also with roughly 20% turndown maximum capacity, is the dual core high speed turbo blowers. Again, this is because you have 2 smaller horsepower units in one single enclosure as opposed to one bigger unit. The second factor for good operation of your blower system to be aware of, again, is that controllability, and it is also not necessarily even the blower technology itself, but it's how that blower fits into the overall system. If we are thinking just of the blower, each of those different blower technology has its own control method. Positive displacement blowers are usually controlled through variable speed control, which means having a VFD that's going to actually adjust the motor output to control the speed of the lobes within the positive displacement blower, which is going to change how much airflow they're putting out. Multi-stage centrifugals have the most varied control methods, so they can do inlet throttling, discharge throttling, or put a variable speed VFD on the motor, or use guide vanes. Depending on which one of those methods your multi-stage centrifugals are equipped with, you might get better or worse control with those. Interleague geared turbo blowers typically come with inlet guide vanes, and also more and more frequently now they have dual point control, so they also have variable diffuser vanes on them. Usually Having both dual point control is going to give the finest control over the output of those blowers. Lastly, the high-speed turbo single-stage centrifugal blowers almost always have variable speed control with a VFD installed on those, and usually that's all integrated into one single package to kind of simplify operation of those, and again, give the finest level of control possible. Once you know how you're actually going to adjust the output of your blowers, you need to decide which indicator you're going to use. Historically, there's two different methods of controlling the blowers, either to a pressure set point or an airflow set point. Historically, pressure was the preferred method, but as Alex will get into, airflow control does usually give more accurate control compared to pressure and is the favored method of doing it these days. Once you have your blowers under control, the real key to getting good operation across your entire aeration system is coordination. So historically, the blower local controls would be provided by the blower manufacturer, but you might have a different systems integrator that is providing the overall aeration control system. So if that's the case, it's very important for those two parties, the systems integrator and the blower manufacturer, to work very closely together so that there's a real good coordination. The blower manufacturer understands what is needed by that systems integrator to achieve the control goals that they've had set for the system. And again, as I mentioned before, we need to make sure that we do have a system that can make those quick, small adjustments to really dial in those DO values right where they need to be. The next step to potentially increase that accuracy is to further integrate the entire aeration system under one supplier, which more and more these days is specified as the blower manufacturer. So most of the major blower manufacturers at this point can supply most, if not all, of the components of the aeration system. So of course you would start with they can supply the blowers. They can then also supply the local control panels. A key distinction to be aware of is whether or not that local control panel contains a PLC or a CPU type board. PLCs are generally more flexible, which might be really critical to achieving those quick, rapid changes. The blower manufacturer can provide a master control panel that can do a number of different functions, whether that's staging, whether that's going to aeration control at a more traditional level using PID logic, or going all the way to the advanced aeration type control systems that, again, Alex will be discussing in more detail. Finally, we can pull the whole system in as a sole source responsibility for the entire aeration system, where now one single supplier is providing the instruments, control elements such as the valves, and then also the diffusers in a single package. That way, everything seamlessly works together with that one source of responsibility. That's all really important because very small errors in the airflow can have a really big impact on the DO. The equation on the left there is the textbook equation that kind of relates the airflow or the oxygen demand that the biology needs with the airflow supplied by the aeration system. There's a number of different factors that account for things like temperature, oxygen solubility, fouling, pressure differences. If all that stays the same, the chart on the right shows how a change in airflow can impact DO. So in this case, this chart is for a DO set point of 0.5 milligrams per liter at that suboxic condition. So a very small change in airflow has a very big change on the dissolved oxygen. So you can see it only takes roughly a 5.5% change in airflow to take your DO all the way from your target of 0.5 milligrams per liter up to 1 milligram per liter. Lastly, discussing the blower efficiency. So in general, positive displacement blowers are the least efficient in terms of wire to air efficiency, although the screw type blowers and the hybrid type blowers with the twisted lobes can increase that efficiency up past 70% and get closer to the efficiency seen by the turbo blowers. Next step up, though, from PD blower in general is multi-stage centrifugal blowers. And then from there, you can step up into the high efficiency of interlead geared turbo blowers and finally into the high-speed turbo blowers. As you step up in efficiency, in general, the capital cost does rise as well. But usually over time, the gain in efficiency is going to offset any increases in initial capital cost. This chart shows some real-world blower efficiencies. This is for a 300 horsepower types of units. And as you can see, The high-speed turbo blowers are generally the most efficient, giving the greatest airflow per kilowatt supplied. Dropping down to the internally geared turbos, slightly less efficient. And then finally, the multi-stage centrifugals are least efficient. And a big thing to be aware of with multi-stage centrifugals, as opposed to the other blower technologies, the multi-stage centrifugals really drop in efficiency as you decrease the airflow, which again, with low DO operation can be particularly critical. Putting that all together, what was selected for Pomona was a dual-core high-speed turbo blower. It has superior turn-down capability against most other blower types. It has excellent controllability, so we're able to really hit those airflow requirements provided by the control system, and it has very high efficiency, so it's really saving the maximum amount of energy possible. For alternatives for plants that aren't able to install new blowers, and particularly new dual-core blowers, then there are some other options. So there can be a blow-off valve that's installed onto the main air header. In this case, we can just vent excess air to prevent increased DO by over-aerating if we can't turn down the blowers as far as we need to. That's definitely going to be cheaper than installing new blowers, but it can be noisy and it can waste energy, which is money. One other option, as we've shown in the picture here, is to install just a smaller jockey blower. So in this case, we have two bigger blowers on the right with the smaller blower installed on the left. That's going to have lower turn down and be able to hopefully meet those low DO airflow requirements. And with that, I will pass it over to Alex, and he can discuss the control system.
Hello? Okay, I'm connected. Okay. Good afternoon. Thank you for sharing with us an hour of that important day for every American. And the goal of my talk today is to explain why precise control is essential for operation. Let's start with looking at the field data from this September from Pomona wastewater treatment plant. As you can see here, ammonia level stayed very low to very close to the set point of 1.5 milligram per liter. As you can see, it was about 1.4 milligram per liter, and the standard deviation was 0.2 milligram per liter. The DO was slightly above 0.7 milligram per liter. On October 1st, the regulatory ammonia limit increased by 1 milligram per liter, so the team decided to raise ammonia target to 2.5 milligram per liter to see whether lower DO possible. Indeed, we, after increasing the set point to 2.5 milligram per liter, the average ammonia was slightly above, as you can see, 2.6, 2.7, and DO was decreased to below 0.7 milligram per liter. So in September, it was slightly above. In October, it became slightly below. The control, as you can see, became a little more tight with standard deviation of 0.15 milligram per liter. What was the most surprising to us, the fact that just 300 to 400 milligram per liter difference in DO under low DO operation, double effluent ammonia concentration. As you can see, again, in September, it was around 1.4. In October, it became 2.6, 2.7. The team, as part of our scope, looked at traditional DO control accuracy using PID method. On average, that control had error of 0.2 milligram per liter, which is 6 times larger than the DO difference caused doubling ammonia concentration, as we could see on the previous slide. So it can be easily concluded that PID control is not accurate enough for low DO operation of the BNR system. As you know, and Natalie discussed that in basin, ammonia concentration reacts very slowly to airflow changes. At the same time, the ammonia load, incoming ammonia load, almost quadruple within just 3 hours. So it can be easily concluded that quadrupling ammonia load and in long reaction of ammonia concentration to airflow change require more advanced control method because PID, as we could see, didn't provide required accuracy. So let's look at the method that's available to us today. While PID method was successfully used for over 100 years across a variety of industries, it has limits, and Natalie kind of touched upon them, which is straight line relationship between, it's assumed less straight line relationship between valve position, airflow, DO, and ammonia. It does not account for all interaction in the distribution system. And it also, the long delay time presents a real challenge for PID control. At the end of 80s, 80s, the practitioners and researchers decided to try a different method that's called model predictive control, or MPC. This method approximates the process using differential equations rather than linear equations, like the PID does. During our trial of MPC at the Chico treatment plant in 2018, we achieved that indeed MPC provides better precision than PID control, although we found that it was a bit slower than PID and could cause occasional oscillations. So later in Chico, we replaced MPC with machine learning method. Unlike previous two methods, machine learning does not rely on mathematical formulas that approximate process characteristics. Using the large amount of data, the computer generates relationship among multitude of process parameters. The challenge, though, lies in finding the match between machine learning libraries such as random forest neural networks, there are thousands of them, and specific control, whether it's airflow, DO, or ammonia. Once selected, the same machine learning library could be used for the same loop at any activated sludge system. Indeed, the libraries that were selected in Chico was successfully applied to the same loops in Pomona. Each of the discussed methods require initial tuning. However, unlike PID, the MPC and ML method can have self-calibrating features, so after initial tuning is completed, the system may operate indefinitely even if external conditions change. Comparison of DO using ML method versus PID showed that the error was decreased more than 3 times and approached the accuracy of DO meters that were installed in Pomona. Ammonia and ammonia, as Steve showed, and DO are controlled by changing air valve position. The most commonly used valves, as Natalie says, are butterfly valves because they are cheap and reliable. But they, as you can see on that chart, have highly nonlinear characteristics. And again, it's a field data and significant hysteresis. Valves are usually moved by quarter-turn actuators. Moving a valve from fully closed position to fully open position takes usually about between 15 20 seconds. As you can see from this slide, it takes 1.1 second to reach 50% of maximum flow from zero. It takes less than 3 seconds to reach 90% of maximum flow. So indeed, this valve has highly nonlinear characteristics. And realizing of importance, precise aeration control and challenges that butterfly valve control present, several companies, as again Natalie showed, decided to change type of the valve and develop valves with linear characteristics. While linear control valves offer superior airflow control at 1% accuracy, their high cost is prohibitive for many plants because the cost is in tens of thousands of dollars versus several hundreds for the butterfly valve. At Pomona, we achieve similar accuracy or even better accuracy than linear valves with the regular butterfly valves by combining butterfly valves operation with machine learning logic. As you know, ammonia removal depends not only on DO, but also on SRT, solid retention time. Precise SRT control is important for all activated sludge systems because it helps to maintain optimum food to mass ratio, the most important parameter of the activated sludge system. Especially it is important for low DO operating plant where optimum performance is required from both heterotrophic and autotrophic populations. The best approach of providing precise SRT control is to continuously adjust waste flow based on constant SRT criteria. The automatic SRT system usually utilizes total suspended solids meters, waste flow meter, and control equipment. Our SRT controller utilizes model predictive method, again, not in this case machine learning, but model predictive, and it consists of those blocks. Inputs, data goes through filtration, because garbage in, garbage out, we need to make sure that the data is trustworthy. Then it goes to the module that does model predictive control. This module calculates the waste flow. That waste flow goes to safeguard module, making sure that when we change the waste flow, we are not only maintaining constant SRT, but we do not cause problem neither with clarification nor with processing waste activated sludge. And then that set point goes to either DCS or PLC. From data from many plants, and again, the Pomona is no different, show that SRT master controller, the SRT master controller that was utilized in Pomona, has about 5% accuracy, which is again approaching the accuracy of TSS meters that were installed there. And it's 5 times more accurate than the traditional manual control. So the results of implementation of all these controls led to significant reduction of energy use. As you can see, we started with the project with 1,300 kilowatt per mg, and we ended at about 550 to 600 mg. Of course, it's a combination of airflow control with the new diffusers and the blower. But altogether, we achieved about 50% savings of energy while maintaining all the compliance with all the permit requirements. But more about this, you can hear and listen and learn at the next webinar where the staff of the LA County Sanitation Districts will discuss how this project was implemented and challenges that we faced and what they would do differently today. Thank you.
Thank you, Alex, as well as thank you to Natalie and Steve. Now we have our Q&A portion of our webcast, and I'd like to invite all three of our speakers to, I see you've got your videos on and you can unmute your microphones. And we've got some questions that have come in during the webcast, and encourage you all to keep those questions coming in now, and we'll start to address those. We had one question come in asking, how do you account for minimum mixing requirement when lowering the airflow rate? And Natalie, I don't know if you'd maybe like to comment on that.
Yeah, I can start that one. So the minimum mixing for requirement is something that's typically considered when we're doing our design calcs, when you're trying to decide on the optimal diffuser count that can meet, your low to high conditions. Us engineers use the rule of thumb, like the 0.12 SCFM per square foot, which is a rough rule of thumb from a textbook value. But we also recognize this can be very site specific, and CFD modeling can be done to help iron out how low you can actually go with that number. There's some papers that show some sites are able to get much lower than that. Otherwise, if you're concerned about mixing, coarse bubble aeration technologies can be incorporated between aeration grids to increase mixing, or maybe occasionally pulsing airflow to each grid to help avoid diffuser fouling are some options that can be used. I don't know if Alex or Steve have any further comments on that one, but that would be my answer.
Well, I just add there's also mechanical mixing options too. So if you know that it's going to be an issue, then you can put a mechanical mixer in that zone.
I also can mention that the diurnal variation of load caused the airflow to change. So even if we had some issues within a couple of hours, based on our experience at a variety of plants, we didn't see any problems, even if we had our minimum airflow was below what's recommended at the textbook.
That's a good point. Like overnight, low loading, you might have lower airflows, but typically that would kick back up again in plug flow processes.
Okay, thank you. We had another question come in. This one's asked, would one of the speakers have any thoughts on pros or cons of placing analyzers, especially ammonia analyzers, in treatment structures preceding biological basins? For example, in the headworks or primary clarifiers, would that have any benefits in terms of the response time?
I can probably answer that question because I investigated it in details. So there are a couple issues. First of all, based on the experience of the industry, placing it up front, especially in primary effluent, the sensor prone to biofouling. And this is issue number one. Secondly, we tried it and we did not see significant benefits for control, but drastically increased requirements for maintenance, and this plant staff was not happy with it.
I'll add to that too. If you put it too far upstream, you might not capture recycle flows. In particular, if you have additional ammonia in your RAS flow or an internal mixed liquor recycle flow that's coming back around that you need to account for in your control system. If you put your analyzer before those flows, you're not going to see those ammonia concentrations.
What we found that using that machine learning method, it kind of captures all this relationship. Thank God we're dealing with a very cyclical process, because people, I'm sorry to say, they go to the bathroom at the same time approximately every day. and they go to work at the same time. So this machine learning method can capture all of that.
Okay, thank you. We have one comment from one participant, a comment on the valves. The comment says the Brits have been using plug valves for a while for aeration control. The valve characteristics are better than butterfly valves for providing aeration control. This idea hasn't seemed to have made much headway in this country. I have one installation where I put these into service on a retrofit. So I don't know if you had any thoughts or comments on that.
Well, again, we showed that the least expensive valves, which are butterfly valves, and quite reliable valves, provided, combining with the machine learning, better than 1% accuracy. I don't think we need to increase the price of installation unnecessary if we can achieve high accuracy control with the less expensive valves.
Yeah, to add to that, so the big advantage of a lot of these other types of valves above butterfly valves is they have a bigger linear range. And so through the machine learning that can learn that nonlinear behavior, you can operate a butterfly valve over that full range and get very precise control with it. So you don't necessarily always need to go to that higher end type of valve.
Thank you. We had a question come in and asks, do you see application of the big bubble mixers for selectors and supplemental mixing?
Natalie, you want to address it?
Sure. Yeah, I'm not sure exactly if you mean at low DO conditions, but yes, I'm a big fan of big bubble mixers for selectors. I've recently learned about some options that would integrate big bubble mixing for supplemental mixing in like low DO tanks, but we're continuing to explore that to see if it's necessary. But yes, we're big fans of the large bubble mixing for selectors in particular.
Okay. I think we've got time maybe for one or two more questions. We had a question come in about maintenance. How much maintenance work is there for the online sensors, especially the ammonia sensors? Yeah, and I didn't know, in particular for low DO operation, do you need more frequent calibration or cleaning, or have you noticed anything along those lines in terms of maintenance?
I invite you to attend the next seminar where the staff will address that question. But my understanding that the meters, the analyzers that were selected, again, they were selected based on long research of various types of analyzers, all ion selective electrode, but from different vendors. I don't think there were problems with maintenance for this particular analyzer versus others, or low DO conditions versus high regular DO conditions. I think the maintenance requirements were pretty limited, although the analyzers are quite expensive.
Thank you for that. And I think we just got about a minute left.
Yeah, I invite you to attend next webinar where people who are responsible for that will address it in more details.
Thank you. That's a good teaser for our next webinar. And thank you to all our participants. We actually have more questions than we have time to answer today. So we will do our best to follow up on those questions and get back to folks that asked those questions. I know we have actually, for those that participated in webcast number 1, we've compiled responses to those and we'll be sending those out this week. So this will conclude our webcast. This is webcast part 2. Thank you all for participating, and special thanks to our speakers, Natalie and Steve and Alex. We certainly hope that all of you will be able to join for part 3, which will be on November 19th. The registration for that is open on the WRRF website, so we encourage you to go there and register if you haven't already. Also, for those of you that were not able to participate in part 1 of the webcast series, that is available for viewing on demand on the WRRF website. So with that, we'll conclude this webcast. Thank you all again, and have a great day.